We're going to look at limits in calculus, particularly ones that end up with the indeterminate form, where we have to use a rule called L'Hopital's rule. Now, if you think back to limits in calculus, there are two types of indeterminate forms that come up fairly often, and that is when we end up with 0 over 0 or infinity over infinity. And of course that includes like negative infinity over infinity or vice versa. Now, there are other indeterminate forms. We are just focused on those two main ones today. So I like to call the indeterminate form with limits in calculus like your red flag. The red flag tells us there is an answer to the limit, but you're going to have to do more work to find it. That could be more algebra, which we'll see in a second, or it could be using another method such as L'Hopital's rule, which we're also going to get to later on in this video. So when I'm trying to evaluate a limit in calculus, the first step always is plug in whatever x is approaching, regardless of what the actual limit looks like. So if I plug in x is negative 1, I end up with 2 minus 2 over negative 1 plus 1, which gives me 0 over 0. That tells me that in the form it's in right now, I cannot determine what the actual answer for the limit is going to equal, because right now we have 0 over 0, and that doesn't necessarily equal a number. That does not cancel out the 1, doesn't go to 0. So this tells me I have to apply more algebra to actually solve this problem. So one of the first things you want to do is look and see, can you actually factor this? In this case, I can factor it. So I'm keeping my limit notation because I have not actually evaluated the limit yet. I'm going to pull out a 2, which leaves me with x squared minus 1, which factors into x plus 1, x minus 1, over x plus 1. And notice you have the same factor on top as the bottom. Those are actually going to cancel out, which on a graph would form a hole, so I'm canceling out the hole, and the hole is what causes the indeterminate form 0 over 0. So if I go back and rewrite what I have, I now have the limit as x is approaching negative 1 of 2 times x minus 1. And now I can go back and try to evaluate the limit. So I'm going to plug in my negative 1, and I have 2 times negative 1 minus 1, which gives me negative 4. And that is my limit. So here's another one. Again, regardless of how it is set up, what I want to do first is go ahead and plug in infinity. So if I plug in infinity, I have infinity on top over infinity underneath. Well, that's one of the indeterminate forms, which tells me in the form it's in right now, I cannot actually determine what this limit is equal to. However, notice your x is approaching infinity, and we learned previously this year that whenever x is approaching infinity, that just forms a horizontal asymptote on the graph. So if I look at what my limit is going to for the actual function, what I want to do is determine what is the horizontal asymptote for that function. So here's my function. And if I look at the horizontal asymptote, we'll notice your degree in the numerator is the same as the degree in the denominator, and based on horizontal asymptote rules, your horizontal asymptote would go to the ratio of leading coefficients. So in that case, this limit is equal to 3 over 2. So a lot of times there actually is no work involved if you know that it's a horizontal asymptote, and that's of course based on x approaching infinity. Now this one, x is not approaching infinity, so I'm still going to apply the same rule where I go ahead and plug in my limit to evaluate it and see what I end up with before I determine what to do with it. So if I plug in 7, I have root 9, which is 3, minus 3, over 7 minus 7. So I end up with 0 over 0. And so that is an indeterminate form, which tells me there really is an answer to this limit problem, but I'm going to have to determine another way to solve it. Now with this one, I cannot factor anything out like I could with the first example. So notice I have a square root, and so what I need to do is figure out how to get rid of that square root. Easiest way to do that is multiply by the conjugate. So basically, I'm kind of rationalizing here, multiplying by the conjugate of the numerator. And so you're going to multiply by the conjugate of whatever side has the square root, because the square root is what is causing the problem. So now, if I multiply this out, I have to keep my limit notation in front because I have not actually evaluated the limit yet. I end up with x plus 2 minus 9 over, I'm not going to distribute on the bottom. I'm going to keep the denominator all written out. Because remember, my goal is to find the whole so I can cancel out the indeterminate form. So here, if I simplify this, this top part turns into x minus 7. Well, notice I have an x minus 7 on top and bottom. So there's the whole, and that should take care of the indeterminate form. So rewriting this limit, I have the limit as x is approaching 7 of 1 over root x plus 2 plus 3, and then just go back and plug in the 7. So now I have 1 over root 7 plus 9 is 3 plus 3. I can drop the limit notation because now I've actually evaluated the limit at x equals 7. And so my final answer would give me 1/6. Now, unfortunately, not every single limit problem can be solved with algebra. And so with the ones that cannot be solved with algebra, where I still have the indeterminate form, I have to use a new rule, which is called L'Hopital's rule. So not all indeterminate forms can be evaluated by the algebraic techniques, thus they invented L'Hopital's rule. And L'Hopital's rule states that if you have the limit as x is approaching, like whatever the constant a is, of a rational function, and that rational function limit results in the indeterminate form of either 0 over 0 or infinity over infinity, which could include negative infinity over infinity, then the limit of the original problem is actually equivalent to the limit of the rational function where we differentiate the top and the bottom. So the limit is x approaching a of f prime of x over g prime of x, provided that the second limit, the latter limit, actually exists or is actually going to be infinite. So this is a great technique to get around the indeterminate form. However, you have to keep in mind this rule only works with limits that result in the indeterminate form, which is why you always plug it into the limit first to figure out, okay, what does that limit actually go to? Because if you plug in whatever x is approaching and you end up with a number, there's no need to worry about any other rule. You already have your limit. But if you end up with the indeterminate form of either 0 over 0 or infinity over infinity, then L'Hopital's rule is definitely a valid way to approach this problem. So again, first step is go ahead and evaluate the limit to see if you get an answer. If I plug in 0, I end up with e to the 0 minus 1 over 0. Well, e to the 0 is 1 minus 1 is 0 over 0. So I end up with the indeterminate form. Notice, though, I cannot factor like I could the first example, can't rationalize and multiply by the conjugate because I don't have a square root. So this is going to be a problem where I would want to use L'Hopital's rule. Now, if you are applying L'Hopital's rule, whenever you say it's equal to the next step, the proper way of writing it is to put a little notation above it that says LH's. That way it indicates to the reader of your paper that you're actually using L'Hopital's rule. So L'Hopital's rule says I'm keeping the limit notation in front, and I'm going to differentiate the top over differentiate the bottom. Well, the derivative of e to the 3x minus 1 is 3e to the 3x over the derivative of x is 1. So you got to be careful. Don't get this confused with quotient rule. Quotient rule is a completely different rule. It's not dealing with limits. It's just taking the derivative of a rational function. This is not the same thing. Once I differentiate the numerator and then differentiate the denominator, then I can go back and actually plug in 0 and see if I end up with an answer. So now if I plug in x equals 0, I end up with 3e to the 0 over 1. Again, e to the 0 is 1, so I end up with 3 as my final answer. So here's another one like that. If I initially begin by plugging in negative infinity, I have negative infinity squared is just positive infinity, over this becomes e to the now positive infinity. Well, e to the infinity is just infinity, so I have the indeterminate form. Definitely cannot factor anything. I don't have a square root, so I can't multiply by the conjugate. Can't rewrite it in any way that would be helpful. So I'm going to apply L'Hopital's rule. So I'm making a note that I'm using L'Hopital's rule above the equal sign. And I'm going to differentiate the top over the bottom. So I end up with 2x on top, negative e to the negative x in the denominator. And now I'm going to see if I can plug in negative infinity and actually get an answer. So if I plug in negative infinity at this point, I have 2x would be 2 times negative infinity is negative infinity over negative e to the, that would become positive infinity. Well, that just gives me negative infinity over negative infinity, which is infinity over infinity. So I ended up with another indeterminate form, which means that the first round of L'Hopital's rule did not actually solve anything, which means I need to go back and apply L'Hopital's rule again. So it's possible you may have to apply L'Hopital's rule multiple times before you actually get to a point where when you plug in your limit, you don't end up with an indeterminate form. If you keep ending up with an indeterminate form, go another round with L'Hopital's rule. So here, if I apply L'Hopital's rule again, I'm going to differentiate the top over the bottom. So I end up with 2 on top, e to the negative x on bottom. And so now if I go back and plug it in, I have 2 over e to the infinity would give me 2 over infinity. Any number divided by infinity, of course, is going to go to 0. Now I have the evaluation of the limit, and so that's where I conclude the problem. With this last example, it begins a little bit differently. So if I plug in infinity, I end up with e to the negative infinity times root infinity. Well, e to the negative infinity is the same thing as 1 over infinity, which would be 0, times root infinity is just infinity. 0 times infinity is actually another indeterminate form. However, it is not an indeterminate form that we can use with L'Hopital's rule. L'Hopital's rule only applies to 0 over 0, or one of the infinities over infinity. So this means I need to go ahead and convert this limit into a form that would give me 0 over 0, or infinity over infinity, so I can go ahead and apply L'Hopital's rule. Easiest way to do that for this problem is to recognize that that negative exponent on the exponential function moves that to the bottom of the fraction. And so now this is equivalent to the original problem, but when I go back and I actually plug in infinity, I end up with infinity over infinity, which is the indeterminate form that L'Hopital's rule allows. And so now I can actually use L'Hopital's rule from this form here. So I'm going to go ahead and differentiate. So using L'Hopital's rule now, I have the limit as x is approaching infinity of 1/2 x to negative 1/2 over e to the x. It's good to go ahead and move that x to the negative 1/2 into the denominator. So I have limit as x is approaching infinity of 1 over, moving the 2 down as well, root x e to the x. And now if I go back and plug in my infinity, I have 1 over 2 times infinity times e to the infinity. Well, all of that in the denominator just becomes infinity, and any number divided by infinity goes to 0. So now I've evaluated my limit using L'Hopital's rule. But from the very beginning, I couldn't do that with that first step until I reformatted it and converted it into a rational function that would end up giving me the indeterminate form of that infinity over infinity, or potentially 0 over 0, depending on the original problem, of course. So just keep in mind, whenever you're using L'Hopital's rule, you can only use L'Hopital's rule if it matches the indeterminate form of either 0 over 0 or infinity over infinity. If it doesn't match that, but you still have another type of indeterminate form, like this 0 times infinity, see if you can rewrite it to a rational function, and then go from there. You could also try factoring, multiplying by conjugate, multiplying by common denominator if you had like a complex fraction. A lot of options are out there. But L'Hopital's rule is a great rule for finding the limit when you want to get around the indeterminate form.